Welcome to ExplainerCast, episode 24. I'm your host, Dave Smith.
And this is Shane Swenson.
And we have some explaining to do. Today, we are going to do a unexpected, unplanned part 2 to our episode 23, which is our very previous episode to this one, on color perception.
Right.
Because something serendipitous happened after we released that episode, or after we recorded it.
Right. Yeah, I hadn't even released it yet, and I was just excited about this topic, so we ended up doing an episode on it, and then we found that there's some other people excited about this topic, and they essentially have performed what I would call an awesome hack in like the engineering sense, where they've hacked the human color perception system in a way that I thought was impossible when we recorded the episode, and I'd love to talk about that today.
Yes, that's so cool. Great serendipity. If you didn't listen to episode 23 yet, I highly recommend you go back and listen to it. Not just because it's always a treat to listen to Shane explaining things, but also because I think it is a prerequisite to this episode. We will probably do a little bit of summarizing, maybe a little bit of catching you up, but I think you're going to want to go deep on human color perception.
Yeah.
And is yellow even a thing? I mean, you just got to go in asking that question of yourself.
Right. And I think in so doing, you'll have a better appreciation for how awesome the work that these scientists at Berkeley actually did. It's incredible work.
All right. Well, I guess you kind of teed up a little bit that we're going to be talking about some new research into how to make the human brain perceive colors in at least in a new way, maybe even brand new colors that have never been seen before, which I would have guessed. How is that even possible?
Yeah.
Why don't you tee it up for us, Shane? What happened?
Yeah, and I'm going to save that just a tiny bit longer. Let's do the bare bones recap, just so that we've at least said the things that need to be said as we go deeper in this episode.
Okay.
Because otherwise it's like, well, why is this special? And so just a quick recap on the way that we humans with our eyes perceive color. We have these special cells in our retina. There are two basic types called rods and cones, and the rods are really there for light versus dark, what's called monochrome vision. And then the cones are where we have our high resolution, fine-grained perception, but they're also the mechanism by which we recognize color. And this is done, I think, biologically in a really cool way, call it another hack, which is that we don't have a uniform ability to perceive every color in what we call the visual spectrum, that color range that goes from red up through violet, red, orange, yellow, green, blue, violet, the colors you see in the rainbow. We actually have mechanisms to essentially measure 3 different wavelengths of the colors in that spectrum, and then essentially interpolate between those measurements to determine which color we think we're actually seeing. And maybe one other thing we have to say as we lay this out is what we perceive as color in physics is essentially a change in the wavelength, or its inverse, the frequency of the light that is hitting our retina. So a longer wavelength, lower frequency light shows up on the red side of the spectrum. And then as you move through the rainbow, through orange, yellow, green, blue to violet, the wavelength is getting shorter. And as a result, the frequency or the oscillations of those light waves is increasing. And so we see long waves as red, we see short waves as blue or violet, and then we see green kind of in between. And again, we don't measure every one of these wavelengths individually in our eye. We have clusters of cones, some of which are specifically adapted to really respond to the red or the long wavelength portion of the spectrum. Some which are on the high end, more stimulated by blue light or the short wavelength of the spectrum, and then some in the middle, which are more stimulated by green. And our brain apparently takes a neighborhood of these cones and takes the relative amount of stimulation by these 3 different colors and essentially says, well, like something like yellow, which is in between red and green, that's going to stimulate both the red and the green to a certain extent. And our brain interprets kind of a balanced stimulation of those 2 cones as having come from yellow. It sort of performs this Occam's razor reduction to what's the simplest answer or simplest explanation for what I'm perceiving. And it'll pick a color out of that rainbow spectrum. And on the upper side, between green and blue, if you're kind of stimulating both green and blue, you get a blue-green, you get like a cyan color that your brain's going to perceive as representing the most likely wavelength based on that relative stimulation.
And Shane, can I just add here that I think for me, the most important takeaway about how the human body perceives these colors from the last episode is that you can trick your brain into seeing yellow, even though the thing you're looking at is not emitting any light with the wavelength of yellow.
Mm-hmm.
Like, it's just got the right mix of red wavelength and green wavelength, and your body goes, oh, that's yellow. Or your brain-eye combination system says that's yellow. And indeed, the screen that you look at on your phone does not emit yellow light. It only emits red light, green light, and blue light, but at varying ratios that makes your mind perceive those other colors.
Yeah, that's exactly right. So in a way, like, I'd say we humans have been hacking the visual perception, particularly color perception, for a long time. Like, color photography essentially hacks this by making some of the, I think we talked about Technicolor, which was a way of doing color movie filming where they essentially captured the scene onto, a red and a green and a blue, or I can't remember if they did red, green, blue, or cyan, magenta, yellow, but they essentially captured it 3 different colors, and then they recombined the light specifically of those wavelengths in order to generate all the colors that we see. And so, yeah, like on your screen, there is no yellow light emitter. Now, in the rainbow, there really is yellow.
Yeah, yellow exists.
Yeah,
right.
There's a wavelength we perceive as yellow, but and if you think about the way your brain's working, when that yellow hits your retina, there's a neighborhood of cones, like even if it's a relatively small spot of yellow, it's going to hit a few cones in that neighborhood on your retina, some of which are red stimulated, and they're like, yeah, I don't get as strong a signal as I would get if it were red, but yellow's close enough, I'm getting something from it.
Yeah, call it like 50% red stimulation strength or something.
Yep. And then similarly, the medium wavelength is green. And similarly, this isn't green light, but the sensitivity of each of these cones, peaks at these primary colors, as we call them, but they span that range. So again, maybe 50% of the effective brightness of that light is sensed by that green cone as well. And then maybe a very small amount or a smaller amount by the blue cone, which is the short wavelength cone. And so the brain sort of takes this information through some crazy analog computer mechanism that we don't understand yet, but maybe someday
it's a series of tubes.
That's
probably
right.
some steam involved.
Yeah, I hope
right
so.
Pressures.
and essentially, it says, okay, if I have, call it equal parts red stimulation and green stimulation, what wavelength would generate that pattern? What single wavelength? And it comes up and says, well, it would be the yellow wavelength, and we perceive that then as yellow. So you can make yellow by shining yellow wavelength light. You can also make yellow by shining the right mix, maybe equal parts red and green, which is astonishing, really. It's such a cool hack.
Yeah, it is so cool. And I think the key there is that these cells, I don't even know which ones, rods or cones.
Cones, yep.
They have kind of a wide bandwidth of frequencies that they can perceive of light.
Yep.
So it's not that they only light up, no pun intended. It's not that they only are sensitive to red frequencies. They're sensitive to red and neighboring frequencies. But the further away you get from the center frequency that they perceive, the lower the stimulation that they transmit.
That's right. Yeah. So they each have kind of a peak where they're mostly attuned to that wavelength. And I haven't studied this. I was thinking a little bit about it. The way that probably comes about is, again, either there's a cellular structure that is sort of size matched to that wavelength, so it kind of highly stimulates like an oscillation or an activation of electron movement or something like that. Or the other factor is each different wavelength of photon has a unique quantum energy level. And so you can also have molecular structures where the amount of energy required to, say, move an electron from like one state to another state is also discrete. And so if you map it so that the right energy level of photonic input matches the amount of energy needed to change, say, the molecular electron state of a given molecule, then you'll find that it responds strongly to that input when it's on target from an energy level perspective, meaning it's on frequency or the right color, and then it responds less strongly, but not zero necessarily, the further away you are from that right color. And so that's how you get this kind of peak and then like diminishing responsiveness to other wavelengths, even if they're the same, call it brightness or power level.
Right. That's an important point.
And related to that, I was thinking about this. If the individual cells had very narrow response curves where they didn't overlap very much, then what would happen would be, as you change the wavelength, let's say you were only stimulating the red, the long wavelength cone, with something near infrared, and then as it moves into the visual spectrum, if it was only stimulating red but at an increasing amount, what you would end up seeing is it just getting brighter. You wouldn't have any information about the change in frequency. You'd just think, oh, there's more stimulation of red, only it must just be brighter red. So very early on in the response curve of red, it's important to start sensing how much green is there, because it's only the comparison of those different color perceptions that allows you to tell I'm somewhere in between. And so it actually works really well that there's massive overlap between the red, the green, and the blue, so that we can truly discern changes in color, not just an increase in power, which we would associate with brightness.
It's awesome.
Kind of a non-intuitive thing, but it's key to how it works.
Yeah, the overlap is key.
Yeah.
Also, if there wasn't overlap, there would be colors that we would just perceive as black, or the lack of color, I guess.
Yeah, you could actually have gaps like in your color wheel where that'd be really strange.
It's like we don't know what's in here.
Yeah.
Other species call this yellow, but we can't see that.
Yeah. Well, and that's a challenge for digital cameras, because digital cameras, actually now I don't know. I'm curious so digital cameras typically a color digital camera will have sensors that are sensitive to red, green, and blue. And what I'm now thinking out loud and have no idea on is what's the bandwidth of the response curve for each of those sensors?
And do they overlap completely, or are there gaps in the... Surely there's no gaps, right? That would be a major engineering flaw.
Yeah, are they engineered to have enough overlap, basically mimicking the way humans view it? Okay, I don't know the answer to that.
You would guess so, because we produce images that look an awful lot like real life.
Yeah, if you had a picture like of a rainbow and it had like a weird little gray or
like a missing
area.
chunk.
Yeah, that'd be a clue.
Or the red just kind of bleeds over into the orange, and you kind of skip orange and go straight to green.
Yeah.
It's like you go from red to lighter red to orange, or to yellow. I don't know.
Yeah, so I think you would have to engineer it similarly, where you have enough overlap in the response curves that you wouldn't miss something in natural lighting circumstances.
Well, there we go. We ventured into outside the boundary of our understanding.
Full speculation.
Yeah.
Okay.
All right.
So there's two weird things to talk about, and that was the purpose that we're going to talk about in today's episode. And that is, by default, if you're thinking about, I have a single wavelength of light, and it's somewhere between red and violet, red and blue, it's going to stimulate the three cones in a physical area on your retina where that light has come into focus in some ratio. And because they overlap, now there are regions where you can stimulate the red and green and not the blue. On the high end, you can stimulate blue and you have very little red and green. But sort of everywhere in the middle, you're going to be stimulating at least two, if not all three, of the different colors of cones in that neighborhood. So there's two things that are hard to do. One of them would be to have a single color of light, a single wavelength, that would stimulate the outer two. So that would be the red and the blue. But yet we think about colors like on a color wheel or on a color triangle that are a mix of red and blue. Like in an RGB system, you can have no green and you can have just red and blue. And like, what kind of colors do you see down in that area, Dave? Have you thought about this? Like, if you have no green and you mix red and blue, do you know what you get?
I mean, in pigment, I would expect a purple.
Mm-hmm.
But in light, red and blue, I can't remember. I used to actually do tech theater lighting, and I knew all these things, but
yeah. So the inverse of red, green, blue, CM.
Oh, it's like a pink. Yeah.
Yeah, magenta, kind of this pinkish, reddish, bluish color that's kind of hard to describe if you really try.
Yeah.
And so magenta is a weird color. And if you go try to find the wavelength of magenta, I don't think you can find a single wavelength for magenta.
Oh. Are there others like that?
I think everything along what's called the purple line, like in a color triangle,
Mm-hmm.
where you're like viewing the gamut of colors you can make using red, green, and blue. I think that line between red and blue, which has these various shades of, red turning to kind of a violet red to a magenta and then to purple before you finally get to blue.
Mm-hmm.
I think that whole line is outside of the standard spectral rainbow of colors that are each a single wavelength.
So that is uniquely a human perception. You can't map it to a wavelength.
Right.
Wow.
So in our visual perception, the way you get magenta is essentially like an absence of the middle wavelength, an absence of green.
All right.
And so you can build pigments that absorb green, and that's what we perceive as magenta. They're still transmitting or reflecting back the red side and the blue side of the spectrum. They're absorbing the middle side. And in light, we would transmit, like in an RGB monitor, you would transmit red and blue, and again, don't transmit green, and then our eye would perceive it as like a dip in the middle with like a higher stimulation on the red and the blue sides. And so that's what we perceive as magenta, and then these other kind of purples that are nearby.
Which is just, it's so interesting that it's not a color. Is it fair to say that that color doesn't exist in nature? In the sense that you couldn't make a material that reflects magenta light, because there is no such thing as a magenta light. There is only the human perception of the gap of greenlessness.
Yeah, greenlessness. Yeah. So if your definition of color is limited to single wavelength, electromagnetic spectral emissions, then that definition does not accommodate magenta, is how I understand it.
There's a ton of colors that don't fit in that definition either, right? Like brown.
Yeah, exactly. So there's other mixes like, brown or tan that are not pure spectral colors. And so, but they're still, we perceive them in nature as something.
Yeah.
And again, this points to how our visual perception is more complex than just a single wavelength identifier, even though that's like the easiest way to talk about it. But as far as we know, all of the colors that humans do perceive are essentially combinations of these three different cones sensitivities plus maybe like just the total like brightness associated with how much total light is hitting your eye. And we actually generate all of our color perception just off of those measures. And it does include this, the interior of that color space where you have a mix of all three that, again, maybe there's no single wavelength that could generate that particular distribution of, that's mixed, but we perceive it as something.
Yeah.
Our brain is used to interpolating.
Yeah. And there's no combination of colors that the brain just rejects, right?
Yeah, not that I know of. Like, I think if you're receiving light and the cells are working as they're supposed to, you perceive it as something. Now, you might perceive it as gray if it's kind of an equal stimulation or power balance stimulation across all of them. And that's what you get, again, your RGB, all three lit up. You're going to get, depending on how bright they are, how much power, you'll go from, black to white, through, a bunch of shades of gray on the way.
Yeah. How many shades of gray exactly? Well, pop culture would say about 50.
That's right. I knew that was coming.
Good.
Okay, so that's like not an impossible color, but it's impossible to do in a single wavelength.
Yeah.
And so now let's talk about this paper. We'll finally get here after all of this lead up.
Yes, back to Berkeley. We're 20 minutes in, and now
Here we are.
we teased it. Now we're ready to hit it.
Yeah. And so the inverse of this is, well, what if you could only stimulate the middle wavelength cone? This is the one that's sensitive to green, between red and blue.
Without stimulating the neighboring, the red and blue cones.
Exactly. And so the reality is that the green and red in particular have a lot of overlap, but blue is in there as well. And so any natural light that's shining onto, again, a sufficiently large neighborhood of your retina is going to hit some of all three types of cones. And if it's in that green range, it's going to stimulate the neighboring cones to a certain extent, in addition to the middle cone, the green cone.
Mm-hmm.
And so that would seem to be the end of the story. Like, there's no such thing as green without red or green without blue, until, again, these folks at Berkeley went and, like I said, hacked a next level hack. Like, if we think of RGB color as transmission is already a hack in the visual system, these guys took it to the next level by going much more fine-grained. Do you want to talk a little bit about what they did, Dave?
Well, I only have a cursory understanding, so I'll take a venture into it, and then you can correct me or take us all the way. But if I'm not mistaken, they generated a green laser, a beam, and they pinpointed the location of the green cones inside of your eye.
Yep.
Some crazy subject eye.
Yeah.
Someone willing to take a green laser into the eyeball.
A wise person once told me, never look into a laser with your good eye.
Yes, with remaining good eye.
That's right. And so some intrepid soul did this.
Yes. And, it's like, hold very still, sir.
Yeah.
Okay.
Yeah. We don't want to miss.
Yeah. So they shoot a green laser directly at the green sensitive cones while preventing any spillover into the red and blue sensitive cones.
Yep.
And it's like, what do you see? I believe is the question that was asked.
Exactly. Yeah. So up to this point, I would say engineers had really good control over wavelength. And again, if we look at our RGB displays, which are just incredible in what they can show us, they're beautiful in their color reproduction. But there was a limit. And I said, you can't stimulate the green only because our eye doesn't focus light into a small enough area to hit a single cone. It's always hitting a neighborhood of them. And that's on purpose. That's how we can see sort of a nice continuous image.
Mm-hmm.
And so, yeah, these guys said, wait, what if we overcome that limitation? We'll turn the laser power down, so we're not going to damage your eye. I mean, I assume they knew what they were doing there. So it's a relatively low power, but it's precisely targeted just to those green cones. So your brain has experienced something it is impossible to experience in the natural world, which is a strong signal coming from the green cone, the middle one, and ideally like nothing coming from the red or the blue, which should have enough overlap that they get something. And here they've got nothing.
So the brain is like, I don't have the matrices to do this math.
Yeah.
Honestly, I'm surprised the brain didn't get a divide by zero error on this.
Yeah. I know. I was thinking about this and I was like, what are the chances you would just end up with like the worst like headache you've ever had or some other like negative, you get nauseated or something.
Like all these floating point exceptions.
Yeah. It's like, you think what you get nauseated when like the signal from your inner ear or middle ear, the one that has like your balance and sort of your inertial guidance system disagrees with the signal coming through your eyes about motion.
Yeah, like virtual reality, for example.
Yeah, yeah. So your brain is kind of doing this like self-checking integration of multiple signals, and this like explicitly violates all of your prior experience and all of your ancestors' prior experience.
Right.
So like the fact that it didn't seem to be a horrific experience is actually kind of impressive. Like it could have gone a lot worse.
Yeah, and so the headline was, someone got to see a color that no human has ever seen before.
Yeah.
And, you read that headline and you're like, nah, that can't possibly be true. I'm pretty sure I've seen every color like, in the range of my life. Nope, you haven't seen this one, I promise. Because only Berkeley has the laser that can make it.
And apparently only like 4 people have gone through the whole process, and we'll talk a little bit about it, to be able to have this experience. And like, if something like the lead author on the paper hasn't done it yet, because he didn't get to do all the steps needed when they had like very limited resources.
Or maybe the lead author was like, are you kidding me? It's a green laser.
Not with my eyes.
This will be the last color you ever see.
That's right. It'll be the best one, but the last one. Good news and bad news.
Yeah, good news, bad news. You'll see a color that no one has ever seen. Bad news, it will be your last color.
And so we've already toyed with the definition of color in this episode. So question, did these people see a new color? Yes or no?
I mean, if the definition of color is anything that can be expressed as a mixture of wavelengths of light, then no. Your body has received photons with this wavelength before. It's just never received them alone.
On the one cone. I should say the one type of cone. Yeah.
Yes, exactly. It's kind of hard to even say this. We just don't have language for this. But yeah, your body has never perceived this configuration before.
Right.
I guess this is kind of like people who are colorblind have actually come closer to this than people who are not.
Right.
People whose cones are not sensitive to certain wavelengths, or who lack the cones that would be sensitive to certain wavelengths,
or lack the differentiation. Yeah.
Yeah, exactly. They're kind of closer to this, because imagine if all you had were the green sensitive cones in your eyes. you would see this color all the time. At least you would perceive it.
Right. Yeah. So in that sense, you're right. Maybe others have actually had this exact experience because of their particular anatomy. But for most people, it's a new experience. And we could quibble about, like you said, it's a wavelength that people have been exposed to before. So it's not a new spectral color.
Yeah.
But it's definitely a new, to them, form of color perception, because it kind of broke the rules again, which are that the neighboring cones get an opportunity to also be stimulated by any incoming wavelengths, and that was denied in this particular case.
So I think I would probably be comfortable saying this is not a new color, but this is definitely a new experience.
Yes, I agree with you there. So let's talk a little bit about that experience. The way it was described is as an extremely saturated color. And by saturated, we mean it's very pure, and it doesn't have like a lot of mixing of like gray into it that would kind of make it seem less intense. So very vibrant, very intense, like pure pigment or color coming into your eye, kind of a blue-green. It looked to me like it's close to cyan. So they had the subjects kind of do a color matching experiment where they said, choose the RGB mix that's closest to what you're perceiving with this. And they kind of came up with an answer that is sort of cyan-ish, but not exactly. But they said it was so intense, they had to turn it down and desaturate it before they could even really make good comparisons to anything they could perceive, like on an RGB screen, for example.
So you're saying that when the human subjects saw this, they didn't really describe it as an entirely new color that they were perceiving, but rather something close to a color that they could describe?
I think, or maybe it was new. Like for sure it was a new perceptual experience. But then they said, okay, what color does this look the most like? And that's where they've come up with, because one of the questions, one of these other kind of philosophical existential questions is, do people see the same colors as each other? We know that, again, with the exceptions of things like a blue-green color blindness or something like that, that by and large, people perceive differences in color kind of equivalently, and we can give persistent names to colors that we've learned, and then we can repeat those. So we know it's like a repeatable experience. We know that this ability to see contrast is consistent, but I don't know that what I perceive as red matches what you perceive, though there's good evidence it probably does.
I think maybe it would be useful if I read a quote from one of the subjects who perceived this color.
Yeah.
They said, "It was a profoundly saturated teal. The most saturated natural color was just pale by comparison."
Wow. So just like way more intense in its perception.
Yeah, than anything you can see in nature.
Yeah.
Which means you probably can't make this color with a standard screen.
No.
Or anything like as intense as it.
Yeah, you could probably get something that you could say, oh yeah, I could believe that you took the same dye and you made a crayon out of it. That's nice. But so like it's sort of wavelength wise looks about right, or wavelength mix, it looks about right. But yeah, it sounds like the intensity of the experience is there's no comparison for that.
Yeah, honestly, when I hear that description, it kind of makes me think of what people say when they're on psychotropics and they talk about how they perceive color very differently.
Yeah. And who knows, like if you had something that somehow diminished the neural pathway for the adjacent cones, like that your red cone was essentially understimulated even when light is hitting it, that could give you a similar experience.
Yeah, if you somehow deadened those cells.
Yeah. So yeah, if you want to see this color, we could either shine a low power laser at your green cones, or we could shine a high power laser at each of your reds.
Yeah, and kill them.
And forever. Yeah.
Now all you get is this new color.
That's right.
And they named it, right, Shane?
Yes. Yeah. Do you remember what they called it?
Yeah, OLO. I don't know if I'm saying that right, but OLO.
I assume so. Did you see why they picked that name? I read this in an article.
Yeah, you know what? As soon as I hadn't thought of it earlier, but now I totally get it. It's like 010, which is like,
yep.
I believe that represents the red, the green, and the blue perception. So it's like
exactly.
0 red, 100% green, 0 blue. That's a pretty cool name. That's very clever. I like that.
Yeah, I have to give them credit for that. That was well done. So we should talk about a couple other details. I think we talked about what it was and what the experience was. why it's impossible. But let's talk about how they did it. So, what does it take? There's a few steps in the puzzle. Like, what does it take to actually successfully hit just your green cones with a laser? And they didn't just target one. They targeted
like 1,000, I think, right?
yeah, all of them kind of in a region of your retina. So you would see an area represented by this, because our eyes again are doing a couple of things. We talked a lot about color perception, where you're computing. It's hard for me not to use metaphors that mean something to me, but you're integrating the information from these three different types of cones to select colors. But we also have tremendous spatial resolution. Like, we can see lines and shapes and discern features that are of different brightnesses or different colors adjacent to each other. And the way we do that is when the image comes through the lens of our eye and then essentially is focused and projected onto our retina, you get an inverse essentially of the field of view coming into your eye, literally hitting the retina. And so dark areas are going to stimulate the rods and cones less, bright areas more, and then in the particular mix of stimulation levels for those cones based on the wavelength. So there's a spatial element to this perception as well as this color perception. And so they targeted the green cones in a spatial area on your retina in order to sort of paint an area in your visual field with this color.
Oh, man. So kind of a monochrome, like pixelated image, I guess.
Well, maybe, except I suspect our eye, again, even though we are receiving discrete bits of information spread across our retina, we interpret the world as a continuous world. And so I think the eye reinterpolates and reintegrates adjacent, call it greens, it merges them. Now, I don't know if like the gap from a red and blue not being stimulated would be enough. I suspect that the eye has enough density that, if it's all red, it doesn't look pixelated. It just looks like red. If it's all blue, it looks like blue. And so I'm guessing it was a fairly integrated, smooth patch of light that they were perceiving in this experience.
And they could probably, I don't know if they were able to vary the intensity of the lasers to make them be kind of like a green scale. That's my word instead of grayscale.
Yeah, like a brightness.
Like a green scale image. Yeah, through brightness.
Right, and turn it down. Because, I think our eye perceives kind of the ratio of that high power perception compared to like the ambient from how bright we perceive something to be. And so I would assume you run it at pretty low power, and if you turn it up a little bit, it would probably get brighter. But with this unicolor stimulation, I don't know how much control they would have had. So how do you make a laser that can hit thousands of cones? And they had a refresh rate. I forget. I saw it like at least multiple times per second. They're revisiting each of these.
Are you asking me how to make that laser? Because Shane, I got to tell you, I don't know.
I mean, I couldn't make it myself either.
Maybe some paper clips. I don't know. Batteries. I'm not sure.
They went through some incredible work. So the first thing is you actually have to know where these particular green cones even are. And every person's retina is different. Mm-hmm. And so this was the reason why there were only like 4 people that have done this. Is the first step is they had to do a map of your retina.
Yeah.
So they take some super high resolution imagery of your retina, and then they run some type of classifier over it to identify where the cones are and to identify which of the 3 types each of them are. So they could say exactly, here's a map of your retina, and we know where all the reds, the blues, and the greens in this little area on your retina actually are.
That's so cool.
Next, you like come up to this machine, and I pictured a little bit like when you go to the eye doctor and they want to take like a picture inside your eye, or they do the little air puff thing and you kind of sit your chin on a thing. I think these subjects maybe had to like even bite onto a bite piece to really like hold their head still.
I read that, yes.
And then stare into the laser and
great idea.
Try to hold still.
Well, that's what I wonder. Like my eye kind of twitches and stuff, and I wonder if how still do you have to hold it? I wonder if they stabilize the eye with something, because I have seen doctors do that. I don't know if they do that for laser surgeries.
Yeah, well, part of this is, and yeah, your eye has these natural movements and little twitches that they do. I think what they ended up doing is they had an eye tracking system, so a visual eye tracker.
Oh, wow.
And so they say they tracked eye gaze translation and torsion with subcellular accuracy
Wow.
using a 960 hertz stream of video strips against the retina map. So they're
Wow.
they're taking a picture like 1,000 times a second and assessing where your eye movement has placed all of the cones they want to target right now, and then they're dynamically targeting this laser to hit again where they are right now.
That's so cool. So you have to bite down to get it close, but then it can figure it out from there.
Yeah, and did the fine tracking.
Even if you kind of move your eyes around. That's so cool.
Yeah, and I guess they'd have some range they can handle, and if you just did zigzag too much, maybe they'd lose it. But
Yeah.
you're probably trying to focus on a target or something as a subject in this.
Just incredible.
Yeah, so we're taking a picture of people's eye. Cool, I've done that at the eye doctor. We're figuring out where your cones are. I've never done that.
Yeah.
Which type they are. And then, to me, the craziest part of all this is where are they right now so I can shoot a laser and hit one and not hit its neighbors.
Yeah, and hit 1,000 of them,
Yeah, and repeat the process rapidly.
Yeah, 1,000 times a second. And the beam forming and the shaping and the aiming is just remarkable.
Yeah, can you imagine trying to calibrate this? Like, no, it's a little purple. It's red. Oh, there you got it.
Yeah. Oh, that's the green.
That's the green.
That's the green I've never seen before.
So, credit to this team. I mean, I'd say this definitely is an unprecedented hack of the human visual system, and cool that some people got to experience it. I think it's helped us learn some new things. Maybe someday people will wear special glasses that project images onto their retina. I think that's the thing people already talk about or maybe do. And maybe someday that will be so precise it can actually synthesize on a cell-by-cell basis what you see.
Yeah. Wow. The whole time we've been talking about this, I've got this image of 50 years in the future, we're wearing like VR-style headsets that are projecting little images directly into the rods and cones on our inside of our eyeballs. So we get the most beautiful, vibrant colors you've ever seen. Way more beautiful than anything in nature. It makes you never want to take the headset off because nature is so drab by comparison.
By comparison. Yeah, another tool in the dystopian future toolbox,
Right.
isn't it?
Exactly. Exactly.
Nature can't compete.
Yeah.
Well, I think we're a little ways away. I think it's super cool in the meantime. And yeah, credit to this team for doing it. And credit to whoever was the first person to say, you can shine the laser into my eye. I'm good with it. Sign the release.
Oh boy. Amazing. All right.
Well, Dave, anything else to cover here? Or have we explained ourselves?
I think we had some explaining to do. We did some explaining, and I feel satisfied with the level of explanation.
Likewise.
Thank you, Shane. It was great.
Yeah, you too, Dave. Good to talk as always.